In Brian Maple's lab at UC San Diego, ordinary matter sometimes behaves in unusual ways.
We're trying to do research at the forefront of science where we don't know what's going to happen and we don't know what properties these materials are going to have. And of course we don't always find something, but when we do, sometimes it can open up a whole new area of research.
Maple's group takes matter to extremes to bring out elusive and unexpected traits. They forge new kinds of materials, then test them under intense physical conditions.
The equipment in this room is for achieving low temperatures in the millikelvin region.
That's just a fraction of a degree above absolute zero, so cold that atoms nearly stop moving. At these frigid temperatures, new physical traits sometimes emerge. One that has captured Maple's interest and that of the world is superconductivity.
Superconductivity is a property that many metals have, and what happens is as you cool them below a certain temperature, the electrical resistivity vanishes and goes to zero, and by zero I really mean zero. They become perfect conductors of electrical current.
Superconducting wires could carry electricity over long distances with no loss. Wound into an electromagnet, the same wires could store electrical power indefinitely, making intermittent sources of sustainable energy, like solar and wind, more reliable.
Magnetic levitation of high-speed trains is the most romantic application.
Trains that float above their tracks would take advantage of the way superconductors behave when they're placed in a magnetic field.
When you cool the material into the superconducting state, the magnetic field gets expelled, so it kind of acts like a magnetic mirror.
Onboard superconductors would create a magnetic reflection to lift the train from its track. But so far, superconductors aren't very useful because they only work when very cold.
So there are lots of things in this room that are superconductors that aren't superconducting because we're here at room temperature. Our dream is to make a superconductor that will go into the superconducting state at or above room temperature, in which case, you know, the world as we know it would be dramatically changed.
The world we know occupies a very narrow range of possible physical realms. Brian Maple's group pushes materials past these limiting boundaries to try to understand how strange traits, like superconductivity, can emerge.
We do this at low temperatures, often at very high pressures, and in high magnetic fields. We want to perturb them profoundly, so to get them to low temperature, you can do this by cooling them with liquid nitrogen, which will get you down to 77 Kelvin, or liquid helium-4, that gets you to 4.2 Kelvin. And then if you pump on that to low pressures, that will get you to about 1 Kelvin. But if you want to go lower than that, then you have to use other techniques, and what we use in this room is called helium-3, helium-4 dilution refrigerators. That gets you down to millikelvin temperatures.
That's colder than outer space, colder than anything we know of in the natural world.
Now for pressures, if we want to go really high, then we have to use diamond anvils. And those are basically two gem diamonds that we press together in a device. And the diamond anvil devices can get you up to megabar pressures.
Close to the pressure at the center of the Earth. By seeing how materials behave in these alien, yet precisely controlled conditions, Maple hopes to learn what factors determine exotic phases of matter. Along
with understanding, hopefully will come predictability, in which case you can then develop a strategy for finding materials with desirable properties. We spend a certain amount of our time prospecting for new materials with properties that will be different and interesting and useful. A lot of what we do is based upon known materials, which we can change by replacing certain atoms by other atoms. So we have a material with a different set of elements. Or we might actually have a hunch that we'll find a material with a certain composition and just try to make it.
In specialized furnaces, they melt novel mixes of elements to forge new alloys, and focus intense beams of light with a polished metal lens to create pure crystals of promising new materials.
We want to basically rearrange the electrons in the solids so that they interact more strongly or differently, or make changes in their crystal structures that might reveal a new property.
It's the structure of the crystal lattice and the arrangement of atoms within it that seems to determine how easily electrons flow. The possibility of unimpeded flow of electrical current has intrigued scientists ever since superconductivity was first discovered in 1911. 75 years later, copper oxides were found to become superconducting at 160 Kelvin. That's warmer than the liquid nitrogen commonly used in science labs and halfway to room temperature.
These are developments that those of us who have worked in superconductivity for our careers at that time thought could never happen, or suspected could never happen. It was really a change, a profound change in this field.
More recently, experiments with iron pnictides have proved promising as well, but these findings are puzzling.
The parent compounds are magnetic and insulating in the case of the copper oxides, and magnetic in case of these iron-based compounds. These insulating and magnetic states can be suppressed, and then once you do that, you often find superconductivity. And so these things, which were once regarded as mutually exclusive, now seem to go hand in hand in many materials.
Magnetism and superconductivity have something in common. Both seem to involve electrons with synchronized motion.
In fact, one of our working hypotheses is to look at materials that exhibit other types of phases, like magnetic phases, that come about because of these strong electron correlations, and then modifying them such that we can move out of this magnetic phase and into a superconducting phase, which may come about because of the same kind of basic interactions, but in a situation where we've changed the conditions and allowed that superconductivity to emerge. I'm pretty sure that as we look at more and more novel materials that we can't even dream about at this point, that the conditions will be such that new phenomena will occur and the properties that we're studying now will be enhanced, and it's probably a good guess that eventually we will get a room temperature superconductor. I don't see any reason why not.